Okay, hello and assalamualaikum everyone. Okay, good morning. I would like to continue our study on our subjects for the BKG 1233, the principles of instrumentation and measurement. Okay, here we are in chapter 4. The title of chapter 4 is the oscilloscope. Okay. So I'd like to make a slideshow first. Okay, so in this chapter, okay, at the end of the chapter, the student we like to students should be able to explain the basic structure of oscilloscope, and second, and student can explain the oscilloscope electronic circuit function, which is inside the oscilloscope there are a lot of electronic circuit, and some of the function need to be understood by the students. And also at the end of this chapter, the student also can use the oscilloscope for signal and phase measurement. And for your information, the outline of this chapter is like this, where first I'd like to explain the introduction of the oscilloscope, and then the CRO, which means the Cathode Ray Oscilloscope Components, CRO. Okay, and then what is the working principle of the CRO? And then we like to go for the Cathode Ray Tube, which is the CRT. Okay, I think nowadays there is not much CRT display, but here we would like to introduce on the CRT. And then how is the vertical amplifier inside the oscilloscope, including the trigger circuit, the sweep generator, the horizontal amplifier, the delay line, and also the probes that we usually use with the oscilloscope to capture the signal. And then the Lissajous patterns, okay, which is commonly used in the analog oscilloscope. And lastly, the overview of the digital storage oscilloscope. Okay, first, for the introduction of the oscilloscope is a graph display device. Okay, I think some of you already know about the oscilloscope because the oscilloscope is like, for example, like the TV, but this only show the graph here. Okay, so anything the signal that you touch with the probe that you are connected with the oscilloscope can be shown and displayed on the screen of the oscilloscope. And the basic instrument, actually the oscilloscope is the basic instrument, okay, for the study to know all type of waveforms. Okay, the oscilloscope can also be known as a cathode ray oscilloscope. The abbreviation is CRO. Okay, and the function of this oscilloscope is to allow, okay, the amplitude of the electrical signals that we are touched, whether there can be a voltage or the current or the power, etc., to be displayed primarily as a function of time. Okay, where for the y-axis you can measure the value of the voltage or the current or the power, and for the x-axis will be function of time, the time taken, okay, while you are measuring the value of the voltage or the current or the power. Okay, the function of the oscilloscope also can be applied to measure such quantities, okay, such as the AC current or DC voltage, time, the phase relationship. Okay, so we can another keyword is here which is a phase relationship, and the frequency, and also the wide range of waveform evaluation. Okay, for example, the phase difference, the pulse width, the delay time, the rise time, and the fall time. Okay, so there are some keywords here, which is the phase difference, pulse width, the delay time, rise time, and the fall time. Okay, let me see what is the delay time. Okay, the delay time is the amount of time, okay, it takes to for the head, okay, for the head of the signal to travel, okay, from the sender to the receiver. Okay, for example, there is a command duty cycle, okay, which is started with this, okay, and then from here there is a delay to started go for the actual duty cycle that have been captured by the device. Okay, the command, this is the output, okay, waveform that come from the time diagram, and this is the actual that the duty cycle have been transferred, okay, from the sender to the receiver. Okay, so this is we call as a delay time. Okay, and for the rise time, okay, the rise time is the time uh, that can go, okay, to rise, okay, from top, from the bottom to top, and for the fall time is the time that can be detected from here, okay, to from the top to bottom. Okay, this we call as a fall time. Okay, the rise time is from bottom to top, and this is another delay where there is a time from the commanded signal to the actual signal to take action. Okay, so this we call as the T of delay. Okay, and then from here there will be a phase difference. Okay, phase difference, and also the phase pulse width. Okay, how many how the what is the width of the pulse in order to know that the time that have been taken for the pulse to on, and what is the time taken for the pulse to be off. Okay, so that's some of the keywords that we need to know while we are working with the oscilloscope. Okay, so as you shown in figure 1, the timing diagram of the PWM signal showing the rise and the fall times. Okay, the rise and the fall time, that the common duty cycle is shown as the logic level, okay, for 0, 1, 0, 1. Okay, while the actual shown is the output voltage with inverted by using the logic level. Okay, so this is the how we know the rise time, fall time, and also the delay time, and also the pulse width and the phase difference. Okay, as the characteristic of the oscilloscope, it depends on the movement of an electron beam to impinge on the phosphor surface, which produce this visible spot. Okay, to 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 display the visible spot, there is some electron beam that come from the CRT, the cathode ray uh, cathode ray tube. Okay, and pollute with the phosphorus surface inside the CRT, and it can reproduce the visible spot on the screen of the oscilloscope. And this can capable of displaying event that take place over periods, okay, over time of microseconds and nanoseconds. Okay, we can capture, okay, the time taken of the signal based on the microsecond and nanosecond based on what we are setting on, okay, based on the trigger or the time. And the CRO also operates on voltage. However, there are other physical quantities, okay, such as the pressure, strain, temperature, and the acceleration also can be measured, okay, by using transducer, okay, to convert the physical parameter to the equivalent voltage. Okay, that means if we use the transducer, we also can measure the other pressure, strength, temperature, and etc. In order to convert it from voltage to the value other physical quantities. Okay, and also we can capable of accepting two or more inputs and displaying them simultaneously. Okay, as you can see in this oscilloscope, there are, for example, there are three inputs. Okay, three inputs that we can connect the probe into this input channel 1, the channel 2, and also channel 3, for example. So we can this oscilloscope can capable to accept two or more inputs based on the model or the type of oscilloscope that we use. Okay, therefore, we can achieve using the split beam or multiple beam tube, okay, that can be displayed on the screen. For example, like this, okay, if we have two screen, two input, so we can see there is a one input on the blue waveform and also on the uh, yellow waveform. Okay, so from here we can know and we can try to compare, okay, either the channel 1 and channel 2 and the relationship between of these two channel. Okay, then we can know that the command signal and also the actual signal are delayed or not. That is a rise time or false time during the compared to the command signal. Okay, so here this is the basic structure. Okay, basic structure in the oscilloscope. Okay, where A is the display. Where is the A? A is here, is the display of the oscilloscope. This can be a phosphorus screen, okay, the green screen, or the LCD. Okay, commonly now the digital oscilloscope are using the LCD or maybe LED, I don't know. Okay, so previously as the analog oscilloscope, they normally use the phosphorus screen. Okay, while when the electron beam collide with the phosphorus screen, the 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 light, okay, will come and show the graph of the signal. Okay, and 4 is the intensity of the trace. Okay, where is 4? Okay, 4 is the intensity of the trace. Okay, if we want to turn up the increase in the brightness, and we can turn up, and if we want to down it, it can be a dimmer. Okay, and the focus control here is set to set the focus on the waveform that we are selected, and the 7 is try to you can control the position of the trace, okay, in order to make sure that the trace are going up or down. Okay, you can control it, okay, based on the Y position, okay, as a vertical. Okay, and 13 is the channel 1 signal input. Okay, 13 is the channel 1 signal input, while 14 is the channel 2 signal input. Okay, and this is where the oscilloscope probe is plugged in. Okay, as a previous picture, okay, you can plug in the probe here. Okay, this terminal into this, and you can lock it, and at the end of this, you can click it to the signal that you want to touch or to measure the voltage or the current or the power. Okay, and then the position of the trace from side to side is controlled by number 17. Okay, the number 17 side to side means the X position. You can change the X position to make sure that it's going to left or right. Okay, you can control it. Okay, so this is one of the YouTube. Okay, that's how you can use uh, the oscilloscope. Okay. Okay. Yeah, I will start again. Okay. This is how to use the oscilloscope when we are trying to measure the AC source. Okay, so this is how we can put the oscilloscope, the probe on the oscilloscope, and this how we can try to use the trigger. So, so means if we are using source, it is channel one, so we set channel. So in order to measuring the voltage, so we can use the vertical. Okay. Okay, this is how we can change, control the position of the vertical. This is for the range, yeah. Maybe see the division, voltage per division. Okay, this is how you can measure the period. Okay. Okay, this is how you can measure the time, the frequency. Okay. 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 That's a thing how we can use the oscilloscope. Okay, based on the tutorial in the YouTube. Okay, so now this is how we can know the basic function inside the oscilloscope. Okay, next, what is the CRO components? Okay, what is the cathode ray oscilloscope components? Okay, so first, okay, the main component of the CRO is the cathode ray tube. Okay, because if we don't have the cathode ray tube, we cannot see the light. Okay, this is the cathode ray tube. Okay, so this cathode ray tube can produce the electron beam. Okay, in order uh, to show the light. Okay, that can be display the waveform on the screen. Okay, and then second is the vertical amplifier. Okay, the vertical amplifier is the first components that come into when the input signal come into the amplifier. Okay, normally the vertical amplifier is near to the probe terminal. Okay, so after there is a vertical amplifier, then there is a trigger circuit. Okay, where the trigger circuit is there is a function to when there is a signal, okay, input into the oscilloscope, the trigger circuit will trigger, okay, to make sure that the electron can be produced, okay, can be shown on the screen. Okay, and there is also a switch or time-based generator. Okay, time-based generator where it when the trigger circuit trigger the signal, the time-based generator can be produced. Okay, and then there is also the horizontal amplifier where the horizontal amplifier is uh, to show the time that can be amplified into a bigger scale or lower scale. And there is an associated power supply, okay, where is there is a HP supply and the LV supplies that can come to CRT, and also for the LV supplies to the all circuit inside the CRT. And lastly, the delay line here is to show that there is to show the delay line on the CRO. Okay, and inside this there is some of the components. For example, the electron gun where the electron beam are produced, and also there is a vertical deflection plates, okay, in order to control either it's going up or down, and also the horizontal deflection plate in order to control either to go for the right or left. And that is a phosphorus screen on the screen, okay, in order to light to show the light from the when the collision with the electron beam. Okay, as the CRO working principles, that is when the signal to be displayed on the screen, it's applied across the Y plates. Okay, across the Y plates of CRT. Okay, so this Y plates, and it will come through these Y plates. But to see the waveform or the pattern, it's essential to split it horizontally. Okay. So that means after that, Y plates, and we'll go to the X plate, okay, in order to show it horizontally based on the time, okay, time taken. And this can be achieved by applying the sawtooth voltage wave to X plates. Okay, then we can see there is a sawtooth wave voltage that can be applied on the horizontal deflection phase. Okay, for example, we can see the voltage signal applied to vertical deflection, and there is a sawtooth wave in order to apply for the horizontal deflection. And at last, we can see the pattern of the signal on the screen like this. Okay, where we can see there is a on the vertical side and also the horizontal side. Okay, therefore, the electron beam would move uniformly from left to right by graphing the vertical vibration of the input versus time. And due to the repetitive tracking of the viewed waveform, the continuous display also can be obtained. All right. Okay, next we'll go for the CRO component. Okay, first, as I already mentioned before, okay, the CRO component, for example, the number one is the CRT. Okay, the CRT is it can emits the electron to the phosphor screen in order to display the signal. And for the vertical amplifier is the wide band amplifier that can also amplify the signal, okay, taken by using the probe to be viewed in the vertical section. Okay. After we amplify the signal, it can be shown in the vertical section. And also for the trigger is to convert the incoming signal into a trigger pulse so that the input signal and sweep frequency can be synchronized. Okay, it can be synchronized. So for the sweep generator, it is used to generate the sawtooth voltage, okay, required to deflect the beam in the horizontal section. Okay, so from the sweep generator, it can be shown together with the time taken to generate the sawtooth voltage. Okay, and then for the horizontal amplifier is to amplify the sawtooth voltage to generate by sweep generator before it applied to the horizontal deflection plates. Okay, as you can see, okay, when the vertical deflection and also the sawtooth wave voltage on the horizontal deflection plates. And for the associated power supply is to provide the voltage that required for the cathode ray tube CRT to generate and accelerate the beam. Okay, so and the delay line is to delay the signal from some time in the vertical section. Okay, this is how we can see the how the CRO components function. Okay, let's see the YouTube here. Okay, this is the block diagram of the CRO. Okay, so that's how the use of the each of the components in the CRO. Okay, so next we are going to the first main important components, which is the CRT. Okay, the CRT is the most vital component, okay, in the oscilloscope, where the CRT is very much similar to the picture tube in the television set. I think currently there is not so much CRT television in this world because we are going for the thin television. For example, we are using the LED by using the plasma and also the LED. Okay, I think in the future there is more important technology. Okay, to make sure that the by using the thin film. Okay, for the television. But the first television is using the CRT, where the CRT makes the applied this signal visible by deflection of the beam, okay, by the beam of the electrons with the phosphor, okay, with the phosphor screen. Therefore, the CRT can show the signal, okay, visible, okay, on the screen. Okay, so then the oscilloscope will depend on the movement of the electron beam striking the fluorescent substance coated screen, which then produces the visible spot. Okay, and the beams are deflected on both X and Y axis, okay, by producing output of time dependent variation of the input voltage. Okay, this is how the signal, okay, can be visible, okay, at X axis and Y axis. Okay. Okay, previously, okay, I think 10 to 20 years before, okay, but this kind of television is a lot in this world, okay, produced by Philips, produced by National, Panasonic, okay, but currently there is no television like this, okay. I think I have one in my computer, okay, 17-inch computer that I bought in Japan during my study in 2002. Okay, I'm still using like this kind of display. Okay, inside of this there is a CRT. Okay, cathode ray tube. Okay, that produce the electron at the back and uh, beam into the front screen. Okay, and there is a lot of electronic circuit inside this, such as the amplifier and etc. Okay, so inside this, we can see there is a heater. Okay, the heater will heat the beam, and the electron hit the cathode, and the cathode will beam the electron, and the electron will be accelerated by using the choke and the accelerator, and the lens will focus the beam. Okay, in order to go for and call it with the phosphor screen. And here there is a steering magnet, okay, in order to control either the vertical or the horizontal, okay, in order to make sure the electron beam can go to the left and right and also top and bottom. Okay, so as the cathode ray tube CRT, there is an electron gun. Okay, as I said, there is a heater. Okay, in order to heat the cathode. Okay, there is a filament. Okay, to heat the cathode, and after that, the focusing. Okay, the focusing is to accelerate the beam. Okay, in order to go until to the screen. Okay, and there is a deflection between the vertical deflect plates and also horizontal deflection plates. Okay, in order to go for the right, the horizontal and the vertical. Okay, and until the screen. Okay, you may okay. So here we can also check the YouTube, okay, video, okay, about the Okay, so that's how the components of the cathode ray tube and the other components are working principles. Okay, so I think you already saw about the electron guns. Okay, how it's important inside the CRT, and it can produce the thin electron beams and etc. Okay, and the beam will deflect. Okay, based on the magnetic field or the based on the for the horizontal and the vertical based on the plus and minus. Okay, because of the electron gun, okay, electron beam that has been produced is a negative electron. Okay, so before that there is a focus, there is a anode, okay, and also the accelerating anode, okay, in order to make the electron beam faster and fast to to uh, to collide with the phosphor screen. Okay, so inside the focusing, okay, there is also a focusing components, okay, after the cathodes, okay, in order to control the grid, okay, we have the control grid here in order to focus it into the first anode, okay, which is we can accelerate the uh, uh, the electron beams. Okay, because the control grid have a big range, and in order to make sure that it's focused and it can be accelerate the speed of the electron beam, then we have the first anode. Okay, and here by using the intensity control, okay, by using the control grid here, the intensity of the light that produced by the electron beam on the screen can be controlled, okay, to make sure it dimmer and brighter. Okay, so this is the power supply circuit in order to give the supply to heat the cathode and also to give to make sure that the electrons are getting dimmer or brighter. Okay, so next is the focusing control is used to control electric lens action. The spot become larger and blurred if it's turned clockwise. Okay, means a dimmer. Okay, and when beams is focused, the electrons are being forced to align themselves in a row and strike at the very same spot of the screen. Okay, so we can see very sharp. Okay, very sharp line, or very sharp point. Okay, other than if we make it blurs, okay, after we turn it clockwise, it can be blur and become larger. Okay, in terms of deflection, the electron beam in the oscilloscope deflect by means of the electric field. Okay, we use electrostatic deflection by positive and negative, whereas the TV picture tubes electron manipulation is most commonly used. Okay, while for the vertical and horizontal deflection plates are used, the electrons are negative charge, therefore they are attracted by the positive charge. Okay, and the field to repel by the negative charge. And in order to move the electron beam in the x and y axis direction, the horizontal and vertical deflection are used inside the CRT. Okay, as the horizontal and vertical deflection direction, we can refer to the simple CRT here. I think we have already shown in the previous video, where H1 is meant by the positive with respect to the cathode, and it attracts the beam and spot move horizontally to the left and vice versa. Okay, because of the H1 is on the left side, so the positive will attract the negative electron into the left side. Okay, similarly, if the V1 is the positive and the spot will come to up, okay, to top, move upwards and vice versa. Okay, if the V2 is plus and the electron will attract the to the positive parts and going to the down. Okay, in each of these deflection, the displacement of the beam is proportionally to the voltage applied at the plates. Okay, if the voltage applied here is stronger, it's become going to the top. Okay, It depends on the positive voltage that given to the plates. Okay, as the phosphor screen, okay, the cathode ray tube emits the electron to the phosphor screen internally to display the signal. Okay, the screen coated with the fluorescent material called phosphor, and this material determine the color, which normally for oscilloscope, blue, green, or blue, green are perfect. Okay, so the material also determine for the trace resolution and trace length of time to remain visible after the signal has ended. Okay, as the vertical amplifier, there is an input signal is fed to the Y deflecting plates. Okay, where through the vertical amplifier. So the vertical amplifier amplify the input signal by using the wide band amplifier, and the gain of the vertical amplifier determines the smallest signal that can be reproduced on the CRT screen. Okay, therefore, the sensitivity of the oscilloscope is directly proportional to the vertical gain amplifier. Okay, if we increase the sensitivity of the oscilloscope, that means the vertical gain amplifier will also increase. Okay, therefore, it is directly proportional. And as gain increase, the sensitivity increase, which allows the observation of a smaller amplitude signal, and therefore the bandwidth of the oscilloscope determine the range of the frequencies that can be observed with the instrument. Okay, this is how the vertical amplifier function inside the CRT. In the vertical amplifier, the wideband amplifier has a precise amplification factor over a wide frequency range. Okay, therefore the wideband amplifier passes the entire band of the frequency. Okay, next, the vertical amplifier consists of several stages, which is here there are fixed overall sensitivity or gain expressed in voltage over division. Okay, so by referring to the figure below, we can see that vertical amplifier consists of several stages. Okay, several stages where the input is fed into the vertical amplifier, okay, and then through the attenuator, so that the last signal may not cause the display to go out to the screen. Okay, so that's to go out to the screen. Okay, this is how the block diagram of the vertical amplifier from the input attenuator until the output amplifier. Okay, go for the plus vertical and horizontal. Okay, so the amplifier here is connected to the first inverter and the driver amplifier, and lastly the output amplifier. As the trigger circuit, here it produces a trigger pulse to start the horizontal sweep. Okay, so in this trigger mode, the input signal is used to generate the substantial pulse that trigger the sweep. Okay, so you can see here by the trigger input, there is a sum of the circuit. Okay, in order to trigger sweep the sweep the triggered signal, and this by using this can ensure the sweep is always in step with the signal that drives it. Okay, so from the trigger pulse, okay, for example, the trigger pulse here, the output waveform will be captured, and we can see there is a sweep period, okay, for the how for the trigger pulse, and also there is a retrace period and also halt off period that have been displayed based on the output waveform. Okay, so in the sweep and time-based generator, if the horizontal deflecting plates are not energized, okay, for example, the electron beam will draw only vertical line in the circuit. Okay, if there is no energy on the horizontal, then it's only the vertical line on the screen. Okay, you can see only the vertical line. Okay, because the horizontal plate are not energized. And the function of the sweep generator is to drive the beam at steady speed across the screen, and the time-based generator produces a sawtooth wave of the same frequency as the input signal to the Y plates. Okay, therefore we can see the Y plates. There is a same frequency that can generate by using the sweep time-based generator. So the time-based generator gives an output sweep signal of the adjustable frequency. Okay, frequency means the time and the frequency are become bigger and smaller. Okay, so that the Y input signal of a wide range frequency can be displayed on the screen. Okay, this is how the sweep generator circuit, okay, inside the CRP. Okay, and there is two important sweep generator requirement where the sweep must be linear, okay, must be linear, and also the spot must move in one direction only. Okay, one direction only. And this recommend call for a sweep voltage having a linear sawtooth waveform. Okay, from here we can see the sawtooth is a linear waveform, and in order to make sure that there is a spot that can move in one direction. Okay, so now we are going for the horizontal amplifier, where horizontal amplifier is to amplify the signal applied to the X plate. Okay, the X plate here, horizontal deflection. Okay, so the horizontal amplifier are given the voltage, okay, in order to amplify the signal either going to left or right on the X plate. Okay, for measurement of voltage and currents, the input to the horizontal amplifier is a sawtooth wave. Okay, uh, so therefore, for the frequency and phase measurement, the input is an external signal where the horizontal amplifier should capable of amplifying both input without the distortion. Okay, so on the delay line, okay, so lastly, the delay line is the purpose of the delay line is to delay the vertical signal. Okay, if we want to delay the vertical signals, we can use the delay line to enough to keep it from reaching the CRT deflection plates before the horizontal sweep circuits are running. Okay, then by using the delay line, when it's not used, the initial part of the signal is lost and only part of the signal is displayed. Okay, so for example, if you want to see there is a only certain part is displayed, and we can use a delay line. Okay, and the other part will be lost. Okay, and this is what the delay line circuit inside the CRT from the main amplifier, and the delay line here will come with the triggered data, okay, the sweep generator and into the screen. Okay, then for the probes, okay, oscilloscope probe may be categorized into two types, okay, where there is a passive oscilloscope probes, where is most widespread use, okay, and it only includes passive elements where may provide straight through connectivity from the point and the test to the scope input, or other types may provide a defined degree of the attenuation. And also there is active oscilloscope probes where the active components incorporate within the probe itself enables greater levels of functionality and higher levels of the performance to be attained. And there is a much more expensive and normal reserved for more exacting or especially requirement for this probe. Okay, there is sometimes passive probe. For example, the one times scope probes. Okay, this is direct probe. We call it direct probe. Is 1/1 ratio. And there is also the high impedance probes where these 10 times scope probes, and also there is 100 times scope probes, but this one not common and tend to be quite specialized. Okay, so this is some of the specification of the probes. Okay, and for the direct probes, 1/1 ratio is the simplest type of probe, is the test lead. Yeah, okay. It does not attenuate the incoming voltage. For a few small wave signal, for example, less than 1 volt, the low frequency application, the typical offer the same input impedance of the oscilloscope, which is normally 1 mega ohm. Okay, where in such CRO has high input impedance and high sensitivity, the test leads should be shielded to avoid harm or low steady continuous sound like that big pickup. Okay, then the input capacitance of the scope and the stray capacitance of the test lead may cause oscillation on the probe. Okay, by in order to avoid this, okay, we have to use the high impedance probe. Okay, where this probe cause a slight reduction in the waveform amplitude and slight change in the wave shape. And to prevent this, the carbon resistor can be used, okay, as shown in this figure, where the carbon resistor can be connected to the shear core in directly to the CRO input. Okay, this is how the probes uh, designed. Okay, for the high impedance probes, where for example 10 times over 1 ratio of the probes specification, it has a better accuracy. Okay, while it have higher levels of the impedance. Okay, where is the input, and we can get adjustable capacitor in order to get better signal and better accuracy. Okay, for viewing up to 200 volts, we can use the high impedance probes, and the transistors are built into the end of the probes that connect with the circuit under test. Okay, where the impedance presented to the circuit under test is increased by factor of 10. And we can enable more accurate measurement can be made by using these high impedance probes. And by using this, okay, there is equivalent circuits, okay, can be used, and the capacitor C1 is adjusted, okay, until the bridge is balanced to get the R1 C1 equal to R in C2 plus C in. Okay, this is how the equivalent circuit formula, okay, in order to get the high impedance probe. Okay, when the bridge is balanced, okay, X and Y are equipotential, and the attenuation of the signal will be 10 over 1. And therefore, the output voltage to the vertical amplifier input can be given as such here, where V out equal to 0.1 V in. Okay, where V in equal to R in over R1 plus R in. And then the C1 must be adjusted to obtain optimal frequency response from probe CRO combination. Okay, from here, by connecting the probe T to the square 1 kilohertz, we can observe the waveform, okay, such as in 4.1 figure, where there is a value of C1 correct, and if the C1 is too small, there is a delay, okay, delay of the and also if the C1 is too large, there is an overshoot, okay, there is an overshoot and become the on the rise on the fall time, if there is an overshoot. Okay, and this is the effect of probe compensation when we are applying on the square wave. Okay, and in terms of the application of the oscilloscope, it can be used in measuring the voltage, current, power, and etc. Okay, in order to measure the voltage, it can be used, okay, peak to peak voltage value displayed on the oscilloscope by observing the vertical attenuator. Okay, so we can see the set of vertical attenuator that have been set on the oscilloscope. For example, voltage per divider, over divider, and using the formula. Okay, for example, we have the signal for A and also B. Okay, for example, for A, okay, A, we can see there is a green signal. Okay, and the green signal, we can calculate how many range. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is a 10 grid, okay, for A. Okay, and we can see, okay, how many on the top, on the y-axis. Okay, so in order to calculate, okay, for the A, for example, okay, we can use this formula where VPP, P over P is peak to peak, peak to peak equal to volts over division. Volts over division times to number of division. Okay, so that means for A, voltage peak to peak is V over division times to number of vertical division. Okay, number of vertical division. Number of vertical division for A is 3.8. Okay, 3.8. We can see here 1, 2, 3, but it doesn't go for 4. It go around through 3.8. So we can go 100 millivolt division times to 3.8 times 2. Why 2? Because it also have the minus part. Then we can get the peak to peak. Peak to peak is 0.76 voltage. Okay, 0.76 voltage. However, for the voltage peak, we can only calculate only for the one part. Okay, if we want to calculate for the voltage peak only, is only one part. We don't have 2 times 2. So therefore, we know that 0.38 volts. Okay, so here we can see that, okay, this is the vertical alternator, okay, for the volt division for the A, and the time division for the on the x-axis. Okay, so an alternator is the device consisting of an arrangement of the resistor that reduce the strength of the radio or the audio signals. Okay, so as for the period and the frequency measurement, in order to measure the frequency of the signal, the waveform must be displayed such that complete cycle. Complete cycle means the complete one cycle. Okay, such that to improve its accuracy. Okay, so here the period can be calculated by using equal to T equal to time over division. Okay, time over division uh, that are set on the oscilloscope and times to number of division per one cycle. Okay, for example, okay, so after if we got the period, so we can find the frequency by using the calculated inverse of the period. We can have the frequency. Okay, so in this oscilloscope, we already have one signal, okay, which is the what we call it, the path. Okay, the one cycle is 16 division, where equal to 1 over 1 millisecond per division. Therefore, the period of this one cycle is 16 millisecond. How we can get this? Because 16 times to how many? It's 1 millisecond division. Okay, 1 millisecond division. Therefore, we can get a period of this is 16 millisecond. Therefore, after we got the period or time, it can be calculate the frequency, where 1 over 16 millisecond is 62.5 Hz. Okay, so here, so we can try to find, okay, the time period, okay, and the frequency for each of these data. Okay, for example, if we said that 1 second, so for there is 4 grid here, 4 times 1. Then we get a 4 second. For the frequency, 1 over f is 0.25 hertz. And at the same time, if we get 2, okay, 2 second, how we can get 2 second? Because 4 times 0.5, because the time division is 0.5 second. Therefore, there is the time period is 2 second. For the frequency, 1 over 2 is 0.5 hertz. And we can go for 1 millisecond. For example, 4 times 1 millisecond, we can get 4 millisecond. And then we can get the frequency is 250 hertz. Okay. So this is how we can find the time period and frequency based on the calculation. Okay, next we can go for the Lissajous patterns, where Lissajous patterns is when two sine waves are applied simultaneously to the vertical and the horizontal plates of the CRO. The shapes, okay, of the Lissajous patterns depends on the frequency and phase relationship of two sine waves. Okay, where the two sine waves of the same frequency and the amplitude may produce a line and eclipse of or a circle depending on the phase difference. Okay, so the Lissajous figures can be depends on the amplitude, okay, the phase difference, and also the ratio frequency of the two waves. Okay, let's see this YouTube first. Okay, we can go for the Lissajous patterns. Okay, that's about the Lissajous patterns. Okay, when there is a XY horizontal uh, waveform together. Okay, so when there is a vertical and horizontal plane on the CRO applied together simultaneously, then we can have the two Lissajous patterns. Okay, that's how when inside the YouTube there uh, he said, okay, the difference frequency of the two sine waves, okay, and shows it simultaneously, okay, XY, and it can show the that type Lissajous patterns. Okay. Okay, so as the phase in the Lissajous patterns, there is a phase measurement. Okay, for example, when we see there is an oscilloscope can be used to find the phase angle, okay, between the two sinusoidal quantities when there is a same frequency and amplitude. For example, if we see there is a y1 and y2, okay, so in order to find the phase angle is based on the sine theta equal to y1 over y2, and we can get the angle. Okay, by determine the angle, for example, y1 is 1.8 and y2 is 2.3, and the solution is y1 over y2 is over 0.783, and we can find the phase angle is 51.54 degree. Okay, so on the other hand, there is a phase angle of the ratio y2 to y1 is 1.25. That means the theta is 53.13. Okay. And another one, if there is a question where the exercise where y1 if the phase angle is 0 and y2 is 4, y is y1. So if you want to find the y1, so we can have the inverse, okay, inverse sine theta. Okay, this is the Lissajous pattern, the phase measurement that we can find when there is the waveform between the Lissajous figure. Okay, we can see there is when there is a waveform like this, and there is a counterclockwise like this, and there is a eclipse. Okay, so when there is a from 0, the angle is 0 until the angle to negative 315 degree, negative 45 degree, and we can find there is a increasing phase shift between the Lissajous pattern that have been shown. Okay, so in this you can see there is a x and y that have been shown simultaneously. Okay, therefore we can find there is a Lissajous pattern that has been shown on the screen. Okay, so for example, if we see there is a x exists in hers is 1 and f exists y exists in 1, so we can see non-stationary is like this. And if there is a 1k, or for example like what we have shown in the YouTube, okay, we can see the stationary like this, and there is a different, okay, different between the 1k for x-axis and y-axis is 1, and we can see only moving up and down on this type of Lissajous patterns. Okay, and non-stationary happen when there is a due to the low frequency, while for the stationary is to high frequency, okay, of the electron beams moving. Okay, for the Lissajous pattern for the frequency measurement, this frequency measurement is to determine the frequency by comparing it with the non-frequency. Okay, we already seen like this in the YouTube where the unknown frequency FB is presented to the vertical plate, and the non-frequency is presented to the horizontal plate. Okay, and here there is a screen where the unknown frequency and non-frequency, and there is a Lissajous pattern that have been uh, based on the difference of the frequency. Okay, and from this frequency measurement, when there is a more complex ratio, okay, for example, 1 to 1, 1 to 2 kilohertz, 1 to 3 kilohertz, then it can be like this. Okay, when there is a horizontal frequency in 3 times that of a verticals, so we can see 1, 2, 3 times of the frequency of the vertical, then we can see the Lissajous patterns is happen like this. And if we can see there is a horizontal vertical frequency ratio 3/2, we can see this 3, 1, 2, 3, and 2, 1, 2, 1, 2 for the for the horizontal. Then we can see that the this kind of Lissajous patterns inside the oscilloscope. Okay, so to determine the frequency from any Lissajous figure, use this formula. Okay, by using the integral frequency, for example, number of horizontal loops over number of vertical loops times the frequency, and we can get the Lissajous frequency measurement. And for the non-integral frequency, we can also find the based on the horizontal tangencies over number of vertical tangencies times the unknown to the non frequency, and we can find it. Okay, so here as I mentioned, okay, we can see there is a 1/1 and 1, 2, 1, so it means 2/1 and 1, 2, 3, so we can see 3/1 and others. Okay, so this is for the integral frequency, and this is for the non-integral frequency. And there is also the Lissajous patterns, okay, with the different frequency. Okay, here the example, okay, for the two sine wave of the equal phase and amplitude are applied to the input terminal of the oscilloscope operating in XY mode. Okay, if the signal applied to the horizontal input is twice the frequency of the vertical, sketch the Lissajous patterns. Okay, so in here we can how we can do that. Okay, we can see there is a vertical input, okay, in twice for FH equal to 2FV, and therefore FV over FH is 1/2. So the signal that can be measured is like this. Okay. Okay, so next is our last part of the oscilloscope, where the overview of the digital storage oscilloscope. In this digital storage oscilloscope, or DSO, is now the preferred type of most industrial application. Okay, because by using the analog CRO is still used by even before all this, it can be replaced due to unreliable storage method used in the analog storage. Okay, by using the digital storage, you can use the digital memory, that you can store the data as long as required without the degradation based on the digital storage oscilloscope. And it also can allow the complex processing of the signal by using high-speed digital signal processing circuit. And by using the vertical input instead of driving the digital amplifier, they digitize by analog to digital converter in order to create a data set can be stored in the memory of the microprocessor. And therefore, the data can be processed and then set to display which in early DSO was a cathode ray tube, but now we can use the LCD flat panel. Okay, so therefore, by using the DSO, we can have the color LCD display. Nowadays is a common. Okay, as you know, okay, the data set can be sent over a LAN. Okay, even we can set the data okay, to LAN or WAN for processing or archiving. Okay, the scope of own signal analysis software can also extract many useful time domain features. Okay, by using the amplifier. For example, here is normal for the analog to digital converter that used inside the digital storage oscilloscope. And from here, we can have many useful time domain features. For example, the rise time, the path width, amplitude, frequency spectra, histogram, the statistic, persistent maps, and everything. We can use it, and it can be meaningful to the engineers in order that have been specialized, for example, in telecommunication, the disk drive analysis, the power electronics, and etc. Okay, so this is how the application of the DSO in the current world. Okay, I think that's all for today. Okay, we already mentioned about the chapter 4 for the oscilloscope that we have already covered all about the CRO until the digital storage oscilloscope. Okay, so here until at the end of this class, I think I have explained the basic structure of the oscilloscope and also explain the oscilloscope electronic circuit function, for example, the CRT, the sweep, the everything inside the oscilloscope. And we also have used study how to use the oscilloscope for the signal and phase measurement, okay, and also the frequency measurement. I think that's all for today. Okay, if you have any question, you may ask me through the Teams. Okay, thank you very much. Okay, thank you.